RS for the right-hand side. The next example will deal with the 3x3 system. 2 times x plus y equals 3 minus z. That's equation 1. Y minus 5 equals 2z minus 3x. And the third equation is 5x equals 5 plus 3y plus 7z. The first thing we want to deal with is to line up the variables so that we have an x column, a y column, a z column of terms, followed by an equal sign, and then the column of constants. This will take some rearranging of terms. This amounts to 2x plus 2y. Bring the z over to the left, and that makes it plus z equals 3. This is slightly different than 1, so we'll refer to it as equation 4. We'll want the 3x on the left under the 2x, and so we'll write 3x plus y next minus 2z equals 5, and that will be referred to as equation 5. In the last one, we have 5x minus 3y minus 7z equals 5, and that is equation 6. As explained before, when we have a 3x3 system, it must be reduced to a 2x2 system, followed by a 1x1 system, where one equation in one variable is the result and can easily be solved for. Then when we have that variable by backward substitution, we can get the results for the other variables, the roots for the other variables. We can either go through a process that eliminates x, and then we'll have a 2x2 system with y and z, or we might eliminate the y variables and have a system that's 2x2 in size containing x and z. We have another option, get rid of the z variable, and we'll end up with 2 equations and 2 unknowns involving only x and y. At this stage, we want to approach the solution in a manner that's the best for us, the most efficient way of achieving our objectives. The variable we want to get rid of or eliminate out of the system is called the eliminant. And the way we decide which variable will be the eliminant is to look at the coefficients of a given set of variables. As for example, if we look at the coefficients of y, the numbers involved are 2, 1, and 3. If we look at x and we want it to be the eliminant, we look at the coefficients and notice that the coefficients involved are 2, 3, and 5. And finally in z, if we look at the coefficients there, they are 1, 2, and 7. It seems the simplest combination of coefficients are those belonging to the y variable. It would be wise, therefore, to choose the variable y as the first eliminant. And this is how we go about eliminating the y variable from the 3x3 system and reduce it to a 2 by 2 system. If we combine equations 4 and 5 as a pair of equations of the system, and in equation 5 we multiply it by 2, 2 on the left, term by term, 2 on the right, you will notice that the coefficients of those two equations for y will be the same. And if the coefficients are identically the same, subtraction will eliminate that variable. So let's do that. I will write the number 2 times equation 5 equals 6x plus 2y minus 4z equals 10. Let's refer to that as equation 7. We will write equation 4 underneath it in exactly the way it's presented here. And so we have 2x plus 2y plus z equal to 3. That's exactly the same as equation 4, so we'll leave it as equation 4. If we now subtract, we're subtracting because the coefficients here are exactly the same. Here the signs are the same, and so I must subtract. Subtracting, I have 4x plus 0 minus 5z equals 7. Let's refer to that equation 8 of the system, since it's different from the other ones. But that's one equation in two unknowns. And I must have two equations in two unknowns. I must have the next equation, of course, with the same variables, x and z. How we obtain that second equation is by selecting any other pair among the three given and eliminate y from that pair. I have made one choice so far, which is the pair 4 and 5. There are two other choices. You may take 4 and 6 or 5 and 6. Out of the three choices, though, only 2 of them need to be worked on. So let's see what might be the best approach. Should we take 4 and 6? The answer is no, because it would involve multiplying by 3 and 2 the coefficients of y. If we pick 5 and 6, the last possible choice, it'll only involve a multiplication of 3. And that would be the wise choice here. 5 and 6. So, continuing then, we'll save this for now. If we take equation 5 and multiply it by 3, write 3 times 5 and get 3 times 3 is 9x. 3 times plus y is plus 3y. 3 times minus 2 is minus 6z. And 3 times 5 is 15. This is a different equation from what we have above, and we will write 9 for it. And now, when I rewrite equation 6, I have 5x minus 3y minus 7z equals 5. And there is the same equation as 6, so I will write 6 beside it. To eliminate y, I must add the two equations. Adding, I have 14x plus 0 minus 13z equals 20. And that's a new equation, and that's equation number 10. Now look at I will write in what I did here, which was to add. Now look at the two red equations here. Each of them belong to the original system, but the 3 by 3 system has been reduced to these two, which is a 2 by 2 system, two equations in two unknowns. Having reached this stage of the solution, you simply have to continue with it as we did in the previous example where we started with a 2 by 2 system and reduced it to a 1 by 1. And so that's how the rest of the solution continues. So I will now continue with the 2 by 2 system, my first reduction of the 3 by 3 given. And I had 4x minus 5z equals 7, equation number 8, 14x minus 13z equal to 20, equation number 10. Now, the eliminant here, for which can either be the x or the z, seems not to make much difference, since the coefficients are fairly involved in either case. There's not much advantage eliminating z as compared to eliminating x. But while you're doing problems of this kind, you should be constantly aware that better choices may be possible. So I will eliminate the z's. If I eliminate z's, it means that I have to multiply equation 8 by 13. So 13 times 8 is 13 times 4, which is 52x. 13 times 5 is minus 65z. 13 times 7 is 91. That's a new equation belonging to the system. We'll call it 11. If I take equation 10 now and multiply it by 5, I have the following result. 5 4s are 20, resulting in 70x. This better be 65z, and it is. And this one is 100. That is my equation 12, and it is a new equation. Each of these equations belong to the same system that I originally wrote. I can now subtract. And if I subtract, I end up with minus 18x, 0 equals minus 9. Therefore, x is equal to plus 1/2. I have my first root. By backward substitution in an equation that only has two variables, and choosing the easier one of the two choices, solve for z. So out of this 2 by 2 system, if I put x into it, I'll be able to solve for z. So substitute. X equals 1/2 in, good thing we numbered them so we can make a reference, and it's in 8. 4 brackets for the x minus 5z equals 7, and 1/2 goes here. 2 minus 5z equals 7. 2 minus 5z equals 7, and solving for z, z is equal to minus 1. We now have the solution to two of the three variables. That is, the solution to x and the solution to z. It's a simple matter to find an equation with three of the variables in it, to substitute those numbers, and find the last and final variable value. We can pick any one of these equations from 1 to 6. Let's choose the simpler one. It seems that perhaps 4 might be the easier one to deal with. If I take equation 4 and say the following: substitute in, 4 is sufficient to indicate that. Substitute in 4, x equals 1/2 and z equals -1. The result is 2 bracket for x plus 2y plus bracket for z equals 3. 1/2 in here, -1 in there. Simplifying, we have 1 plus 2y minus 1 equals 3, and y is equal to 3/2. There you have the solution in alphabetical order of the variables. X is equal to 1/2, y is equal to 3/2, and z is equal to -1. And now we want to use the same format as I did earlier with only two variables. That is to say that x, y, z is equal to, in the same order now, 1/2, 3/2, and -1. The next method of solution will be by graphing. I will give you a brief description of the Cartesian coordinate system. Sometimes we refer to this system as the Cartesian plane, or simply the rectangular coordinate system, but it is more commonly referred to as the Cartesian coordinate, in honor of a French mathematician of the 17th century whose name was René Descartes. The graph consists of two lines as reference lines, one drawn vertically and one drawn horizontally, right angles to each other. The vertical line is referred to as the vertical axis or the y-axis. And so we'll use a capital letter Y to indicate the name of that line, of that vertical line. The horizontal line, or the horizontal axis, is referred to as the x-axis, and I will draw a capital letter X for that. The point where the two lines intersect is referred to the origin and is given the letter O, which is also a reference point with a value equal to 0. Beginning with the x-axis, what you want to do is scale it by drawing vertical lines of equal intervals, as you see here. We will use a scale in which this first point has a value 1, this one has the value 2, and so on, 3, 4, 5, 6, etc. You could use a scale in which these are 2, 4, 6, 8, 10, for each, or maybe even 5, 10, 15, 20, 25, 30. You must be consistent in your scale on a given axis. Scale both axes the same. Also, do a minimum of writing when you label the, or at least when you scale the axes. In other words, I would suggest that you do not do something like this, 1, 2, 3, 4, 5, all across the x-axis, but perhaps do something like this. 2 for this one, 4 for this one, 6 for this one, etc. Or even every fifth scale here should carry a number. So from here to that particular mark on the x-axis is 5. Now, going towards the left on the x-axis, of course, we have 1, 2, 3, 4, 5, and this is -5 in the opposite direction to +5, equidistant from 0. 1, 2, 3, 4, 5, and 1 over too many. Didn't think that looked right. The vertical axes are scaled similarly, and so I have 1, 2, 3, 4, 5. Of course, that's 6, 7, 8, up to 9. That's the limit of my graph. I have 1, 2, 3, 4, 5, -5, -6, -7, -8, -9, and so on. Now, if these axes are drawn on grid lines of your graph paper, and each of these marks along the axes follow grid lines themselves, then each grid point can be referenced to the scales that I've used along the x and y axis. In other words, if I go to the right 1 and go up 1, then this point can be referenced by the coordinates 1, comma, 1. 1 for going in the direction to the right 1 position, and the other one going up 1 unit vertically. So 1 is referenced to the direction x, and the other one is referenced to the direction y. If I took this point here, for example, which is 1 unit to the right and 3 units up, I would reference that point by using the coordinates 1, comma, 3. If I was as far out as 5 here and 7 up there, then this particular point would be referenced by the coordinates 5, comma, 7. You have to maintain consistent order in the manner that the numbers are written within the brackets. All that you see here is part of the reference to the point. In other words, you have a bracket, a number, a comma, a number, and then followed by a closing bracket. This origin, of course, is 0, comma, 0. If we go way out here to -4 and up 1, then we would reference that point by the coordinates -4, comma, +1. So every point in the system where, if, as I explained, you're using graph paper, every grid point would be referenced by the whole numbers, or I should say integers, that are used on the scale of the graph. And of course then there are points in between that too, within the squares, which would then be fractions. Here's another, let's choose another point down here. If we go towards the left 2 places, and down here 3 units, get it a little bit lower, then I would reference that point by using the coordinates -2, because that's how far I went over to the left along the x-axis, comma, -3. So any general point on the Cartesian plane is referenced by an x value followed by a y value. This is sometimes referred to as the x-coordinate or y-coordinate. The x here is referred to as the x-coordinate or abscissa, and the y-coordinate or the ordinate of the so-called ordered pair, by the way. This is referred to as the ordered, because there's a certain order that those numbers must be written. Only a 2 by 2 system will be considered in solutions by graphing. Let's take, for example, x plus y equals 3 as our first equation. And x minus y equals 1. We already have solved systems like this one algebraically. The first step is to organize what we refer to as a table of values. You must construct a table of values for each of the equations given. And the table of values for x plus y equals 3 is as follows. What you must do is draw up a sort of table like this, where the top row of numbers will be the x values and the bottom row of numbers will be the y values, referring to equation 1. I'll put equation 1 here beside that table to remind you of it. We set up 3 boxes like this, and we make any choice for x that we want to. There's no restriction for the value of x chosen. Take convenient numbers for x, by the way. You don't want to use fractions if you can avoid it. So I'm going to stick with just ordinary integers. For example, like -3, 0, and +3. 0 is always a favorite number in making up tables of value.